Good afternoon, everybody. I just want to start out by saying, as much as I come here to give a keynote talk, I learned so much from so many panels. I was getting re-educated. And it's one of the benefits of being at these conferences. The second objective of my talk today is to give you hope that these complex diseases, starting in Alzheimer's, Parkinson's, ALS, are all going to fall to our axe. And I'm going to demonstrate that today on just one of them for Alzheimer's. I'm also here because I'm trying to bring the cutting edge of precision medicine to the Middle East, and I'm soliciting partnerships in the MENA region, and particularly headquartering it in Dubai. And the fourth thing that I'm going to show you is an entirely new way of how we are approaching complex brain disorders, because the brain is inaccessible. And so we've been hampered for the many centuries, being unable to understand what actually causes Alzheimer's and then how do we actually treat them. So our core objectives is early diagnostics and therapeutics. And when I mean early, I mean very early. So our approach is pretty much what you can see here. The pointer's not working. We start with human models of the brain. We use mathematics. Some people euphemistically call it AI. We don't. It's mathematics. We understand mechanisms. Then we are able to identify targets and molecules that then become medicine along the traditional trajectories of development. And finally, they reach the clinical markets. And that's what I'm going to demonstrate, that we are just one step before the markets for Alzheimer's. So what is the issue? The issue is on one side, it's the patients, the suffering, the loss of family, the loss of cognition, whether it's Alzheimer's. In the United States, it costs $150 billion a year in caregiving. It's tanking our financial ability to be a nation. It is not even trivial. Parkinson's is one of the second most prevalent disease. Autism. Today, the rates are so high, and it's even higher than 1 in 36. It's down to 1 in 17. And it's exhilarating, and we don't really know why, okay? It's a very scary place that if all our kids are going to become affected by this disorder and we don't get a handle on it, it is a doomsday scenario coming. Then comes opioid addiction. It has killed over 1 million people in the United States, and it relentlessly continues to take lives and terribly affects the functioning of society. And then finally, aging, because demographically the world is getting older. So all of the age-related diseases are also exhilarating, leaving us in the next 20 years in a very, very difficult situation as far as brain disease are concerned. So what invention was necessary? And that is something we did back in 2015. We were widely covered by the press, CNN, BBC. I engineered the human brain from skin cells in the dish. It's complete. It's got the retina, the spinal cord, it's got everything, the blood-brain barrier. It is I would say, a living brain outside the brain. And I can do it in anybody. And the most useful ways we do this is when we start to take the donors from those affected with a given disease, be it Alzheimer's, Parkinson's, or anything else. So that produces regulatory grade molecular data. What do I mean by that? It'll pass the FDA in the United States, and I'm going to show you how. So 90% of medical AI, and we heard many AI panels over here, they suffer from a bottleneck in medicine. They cannot get regulatory grade anything. EHR records don't cut it. Unreliable and huge liability in the field of medicine. So AI cannot be just trivially applied as much as people want it to. But we build the biology and the molecular markers that teach AI to be intelligent, okay? So how do we do it? We take skin cells, that's the process, and you can see these little white dots in the dish. Those are the brain models, and that's what it looks like. It's got everything from the retina to the cortex, the spinal cord, the top to the bottom. Everything you can imagine is in there. And this is just data, because we like to show data, and we may not be able to see it below the chairs, but that semicircle is essentially showing you that we have molecular data for all the biomarkers for every region, including the immune system, which is the microglia in the brain. We also show data that all of the key biomarkers at the protein level are expressed in the right areas of the brain. These are immunohistological data that gives you confidence that what we're saying is actually true. So now we're getting down to the breakthrough has a predictive accuracy of 85%, and I'll show you some of the data. So we go from pattern recognition to true biological intelligence, not artificial intelligence. So we collect about 15,000 biomarker data points per disease, per model. We have the data actually fully corroborated by human postmortem data, human genetic data. Also, we have the data corroborated by fluids we get from patients, living patients, which include urine, CSF, and plasma. There they do them in proteins. The genes for them are actually dysregulated in our model system. So we have now taken a harmonization between a bioengineered brain and the actual human brain and the actual human patient, and we're showing that they are overlapping in huge ways. So now we have the confidence that what we do here will apply to the patient. The reproducibility is 99% at the bottom. It's regulatory compliant. We have been funded by the NIH and by the Department of Defense in the United States. So we have gone through peer review of all our stuff and actually been given awards, financial awards to do cutting edge research. So what does the data look like? This is the key to AI. Oops. On the left panel in pale blue is gene expression data, and you see these graphs. And on each axis is a random brain model from about 1,000. And we look at it throughout development so that they reach maturity. This is a timeline at 12 weeks. You see this straight line? There are 15,000 points on it. It has a R-squared coefficient of 0.94 to 97. And on the right-hand side, we are looking at the metabolites from the same thing, and that is high-field NMR. We can measure about hundreds of metabolites, and the two graphs, one below the other, one red and blue, are two independent samples. And what you see is they are 99% identical. So now you see the power of molecular data. I can look at how genes change, and I can see orthogonal validation in metabolites on the other side. And they must be in coherence. Only then we have confidence that we are actually measuring changes, one caused by the changes in genes, the proteins, and ultimately in metabolic pathways. This is the foundation for how AI will become powerful. Without that data, AI is not intelligent. So we have precision, we have accuracy, which is it's corroborated by human condition, it's reliable, and it's scalable. So we can do thousands of experiments over and over and over, get data in the billions, and what that allows us to do then is to start to teach algorithms, mathematical algorithms, how to use the data and find the sweet spot of coherence in a mathematical model. Now, what does that do? Well, on one side, it has huge effects on predictive health. And it can be used in SaaS applications where you can mine the data for lots of different things that you want, disease by disease, condition by condition, all of the variances you need, be it nutrition and the environment, all can be done in the model without a human being involved, because this is a model of yourself. And that data is now used in predictive health and therapeutic acceleration. That is, we find the targets that are actually driving the disease and ultimately drugs. So here is that same kind of data on the left-hand side. I've shown you the graphs for normal, and on the right-hand side is Alzheimer's. Today, I'm going to focus just on Alzheimer's, but trust me, we can do this and have done this for just about every brain disease. And we are moving at lightning speed towards solving most of these brain disorders. So on the top graph is a familial form of Alzheimer's, and the bottom is a sporadic form of Alzheimer's. We get very similar kinds of metrics. Now, here's how we start to create coherence. We have 4 models, APP on the left. Some of you know that's amyloid precursor protein, PSEN2, another familial form. On the right-hand side, one of the most prevalent forms called ApoE4, and in the bottom, sporadic. They overlap with postmortem brain for 500 biomarkers or more. So then we ask, what is common to all 4 of them? And then from that, we are able to get the early diagnostics and most powerfully, bottom drug targets. So using such a strategy, we now have discovered that Alzheimer's is not what pharma has said, and not what the KOL have said, and not what anybody has said. In fact, what is driving Alzheimer's is inflammation and glymphatics. If you don't know what glymphatics, it's the perivascular system around your brain that washes out when you sleep all of the metabolic waste, and it drains it. So basically, think about it as your toilet that flushes the brain every 24 hours so that all the metabolites that accumulate in your brain every day is washed out, okay? And that is dysfunctional in our models across all 4 models. So it gives you a sense that there's truism regardless of which model we pick. Now, we then use mathematics, not AI. I don't want to use the word AI. And we took large data sets, hundreds and hundreds of biomarkers, actually thousands, and we asked, what is upstream of all of this stuff? And we found the targets. They call target 1 and 2. We can't disclose them yet because they are in patents and other things. And then we asked, if we were able to identify small molecules for them, the prediction would be that all of those biomarkers, you can see them, you can't see them in small print, and they're very well known drivers of glymphatics and inflammation. So if they're, say, upregulated, they should be downregulated with the drug. And if they're downregulated, they should be, so you should shift the polarity. Only then you know you're driving a cure. And that's exactly what happens. Every one of them changes polarity with our drugs. So for the first time, we believe that one strategy to actually address Alzheimer's is to address an intrinsic inflammation and an intrinsic inefficiency of the glymphatic system that is actually at the root of the stuff. And we did this 10 years ago, okay? Trust me. Today, if you look at the modern literature on Alzheimer's, through MRIs, they're saying the same thing. Oops, we have a problem with the glymphatics. So beautifully, we are always 10 years ahead of just about anything that appears in the clinics because of the strategies we employed. So now, we've gone way beyond that. In our models, we do therapeutics. This is metrics of what this means in terms of markets. This is typically for investors, not for a lay audience. And we have drugs for Alzheimer's, Parkinson's, aging. Very big surprise, aging. Migraine, which affects women primarily. Therapeutics. In the middle, we have now used and built the model for an accelerated aging disease called progeria. These poor kids are born old. They typically die by the time they're 12, 13 years old. We did the modeling and we replicated what is called the hallmarks of aging. So for them, therapeutics is coming, but more importantly, it opens the door to ask, can we mitigate the fragility and the osteoarthritis and all the other things that happens as most of us age? Some age better than others. Those who live in the blue zones tend to not suffer from all the consequences. Why? And others succumb to that early in life and live a very terrible life. And so we are saying, can we shift this whole thing to further and further down? I'm not claiming I'm God and I'm going to give you infinite life. I'm saying I'll make you live as healthily as you can to the maximum lifespan of about 100 or 120. That's the strategy we're trying to bring to market. And at the end, a lot of AI panelists were here. We're also involved, but our approach is it's the data. Make sure the data is precise, it's accurate. Then you implement an algorithm and the outputs will be reliable, regulatory grade, and can be actually brought into practice in medicine. You cannot hallucinate on a patient. They're going to die. This is life and death. You can hallucinate on a silly essay and there are no consequences. In the world of medicine, it has to meet the highest metrics of regulatory agencies, and that's what we're bringing to the market. So overall, in summary, we go through that standard models, mathematics, mechanisms, molecules, medicine. Going down from top to bottom is the things we have done. The preclinical ones have small molecules over there. All the other ones that we're doing, opioids, autism and all, are just one step short of that. But we believe that the approach has now reached a scalable and very stable strategy. It's just a matter of time before we move this, and we can do new things. ALS, which we haven't done yet, Huntington's, and we believe that, what I'm trying to say is there's real hope that real molecules in the real world are going to come from our company. So, end of the day, I'm just summarizing this. I showed you the data for Alzheimer's. I'm showing you now for the first time the data that we have for all the hallmarks of aging from a patient donor that had progeria over there in the middle. And at the end, I won't get into the complexity of what we're solving. On the left-hand side are what are called gene regulatory circuits, and on the right-hand side are the metabolic pathways. Extremely complex, but we are able to deconvolve them using our strategy so that we go from functional genomics all the way up to what they call phenomics, which is behavior. In Alzheimer's, it would be cognitive failure. In Parkinson's, it would be motor tremors. We are able to scale across all of them within our model. So, end of the day, we can predict the disease before the symptoms appear. We can identify the drivers in real time. This is how good we really are now. We are at 85% efficacy. We can detect Alzheimer's and Parkinson's 20 to 40 years before you even know you're on track to get Alzheimer's. Nobody else can do that. The closest they come with blood tests is typically 10 years around MCI, mild cognitive impairment. By then, I'm going to tell you, the truth is, it's too late. For all interventions that are not drug-related, you want to be very early on because there are other ways, and I told you about them. There's nutrition, and there's the environment. And the environment can be trauma, the environment can be metal ions, the environment can be pesticides. They can, all kinds of things contribute towards a trajectory across your lifespan towards disease. In women, particularly, perimenopausal and menopausal changes actually take Alzheimer's into a highly debilitating state. We're addressing women's health too, so that we catch it early and they don't suffer as much as women do compared to men. So we are big in women's health too. And so, drug repurposing, precise discovery, faster regulatory, these are the advantages of working with us. The FDA today has mandated no mouse, no chicken, no rat, no marmoset, all humans. We were 10 years ahead of them. We set the standards, they're following. We lead, they follow. And we are the only ones with a patent on it. So from a commercial standpoint, we are sitting very pretty. And so this is the trajectory, a decade. This has not happened overnight. It's taken over a decade to do. We have a US patent, the FDA mandates. Other people are jumping in now saying, oh, we're going to do humans. Well, in the brain area, we are already 10 years ahead of you. So what's the thing? The attrition reduction is 60%. Months to approval on a regulatory is 6 months faster because the FDA now wants human. And our translational error, that is between species, we are at 99% better than anything ever done in this field, which is mostly mouse and rodents and things, which, honestly, I've told other conferences, I jokingly said, in my laboratory, I sent Minnie and Mickey Mouse back to Disney. Okay, it was a quip to say, what made you think we are mice? For all this time in medicine and doing all this stuff and wasting money, time, and people now are at a cusp of severe problems because the medical system failed very badly. And this is who are supporting us. I want to acknowledge our chair is Lord Mark Reardon. He's from the royal family in Monaco. It's the Sully Family Trust that is backing us. We have other very big family offices backing us. Very lucky. But they do recognize the value of what you're bringing. On the right-hand side is a very smart South African he was actually a fellow of the Royal Society of Medicine in the UK. He's our chief medical officer. We have a very talented team of people. We have AI, electrical engineer, mathematician on the left, stem cell in the middle, former Merck to do drug development, somebody who worked in CVS, and Dr. Clay Marsh, who's the dean of the West Virginia Medical School, and he's an expert in precision medicine. So with a beautiful team working in sync, and I'm recruiting others, by the way. This list will get even bigger. Some of us from Dubai that have volunteered to be partners at this meeting. I've networked. We will work together to solve complex problems because we're all human. When we work together, we solve big problems and hopefully change the world. And so the future is medicine. It's human, but it's powered by AI, not the other way around. And finally, this is a call for partnerships, particularly in the Middle East, in the MENA region. We are looking for those who want to participate in our investments. What we are going to use the money for, scale and validate, develop early diagnostic tools, preventative strategies so that you don't succumb to this. We are addressing everything from gender, ancestry, nutrition, environment, all within our model because they're not going to be the same for everybody. Trust me, I mentioned the blood test that they brought for Alzheimer's doesn't work in African Americans. There's a big problem. So this is how you will partner with us, invest in us, co-develop solutions, license our models, integrate with our API. That's me. My contact information, I welcome inquiries. Partner any way you want. Thank you.